Hello, welcome to 3.9, Differentials. Linear approximation. So in the last section we used Newton's method to approximate zeros. Now Newton's method relied upon the use of tangent line to a graph in order to approximate the graph. In this section we'll further examine other situations in which the graph of a function can be approximated by the use of a straight line. So consider a function that is differentiable at point C. The equation for the tangent line at point C, f of c, is given by y minus f of c, or think of y minus y1 equals m times x minus x1. So y minus f of c equals f prime of c times x minus c. It's utilized in the point slope form. So y equals f of c plus f prime at c times x minus c. So because c is a constant, y is a linear function of x. We get a line from this. Furthermore, by restricting the value of x to be sufficiently close to c, the value of y can be used to closely approximate to however close the user wants it to be, the values of the function of f. That is, as x approaches c, the limit of y is f of c. So here's example 1. It says, find the equation of the tangent line L to the graph of f at the indicated point. Use this linear approximation to complete the table. So f of x equals x to the fifth at the point 2, 32. So be like we have our f of x values and we'll do our t of x. These are our approximations. So first of all, what is f prime of x going to be? That's going to be 5x to the fourth power. So f prime of 2 is going to be 5 times 2 to the fourth power. 5 times 2 to the fourth, that's 5 times 16, which is 80. So we'll say y equals 32. This is our f of 2 is 32. So 32 plus 80 times x minus 2. Or y equals 32 plus 80x minus 160. So y equals 80x minus 128. So we're using the y equals f of c plus f prime of c times x minus c. That's what we've done here. So we'll fill in this table. So 1.9 to the fifth power is 27.761. 1.99 to the fifth power is going to be 31.208. 2 to the fifth power we know is 32. 2.01 to the fifth power is 32.808. And 2.1, it'd be 40.841. So this row here represents the actual values. Now we'll do our approximation. T of x equals 80x minus 128. So if we put in 1.9, we get 24. Put in 1.99, we're going to get 31.2. Put in 2, we're going to have our 32. So we're right on here. Pretty close here. It gets a little further there. If we put in 2.01, we have 32.8. To put in 2.1, we're going to have just 40. So it's an approximation around 2. It's fair. It's not great, but it's fair. Okay, so we're going to go on to page 2 now. This is the definition of differentials. Come on. There we go. Let y equals f of x represent a function that is differentiable in an open interval containing x. The differential of x, denoted dx, is any non-zero real number. The differential of y, denoted by dy, is dy is f prime of x dx. So in many types of applications, the differential y can be used as an approximation. This differential will be an approximation of the change in y. So delta y is approximately dy, or delta y is approximately f prime of x dx. Delta y is really related to our delta x. So use the information to evaluate and compare delta y to dy. Here we have y equals x to the fourth. Plus 1, x equals negative 1. Delta x is dx, and that's 0.01, so that's okay. And just to note, delta y is going to be equal to y2 minus y1. And y2 is f of x2. And y1 is f of x1. So our delta y would be f of x2 minus f of x1. Now what is x2? x2 is x1 plus delta x. So this would be f of x1 plus delta x minus f of x. So here our y equals f of x, which is x plus 1, x to the fourth plus 1. F prime of x is 4x cubed. So we need that for our dy. Because dy is f prime of x dx. It's going to be f prime of negative 1 times 0.01. It's going to be negative 4 times negative 1 cubed times 0.01. It's negative 4 times 0.01. That's negative 0.04, and that's our dy. Now for delta y, as I said above, it's going to be f of x plus delta x minus f of x. And that's going to be f of negative 1 plus 0.01 minus f of f of negative 1. That's going to be f of negative 0.99 minus f of negative 1. So that's going to be negative 0.99 to the fourth power plus 1 minus negative 1 to the fourth power plus 1. That's going to be 1.9606 minus 2. That's 1. 1 plus 1 is 2. And we have negative 0.03404. And that's our delta y. So our dy is negative 0.04. Our delta y is negative 0.03404. No, pretty close. Okay, next thing we're going to talk about is error propagation. Error propagation is common for engineers and physicists to make common use of the approximation of delta y by dy. One example of this is in the estimation of errors propagated by physical measuring devices. If you let x represent the measurement value of a variable, and let x plus delta x be the exact value, then delta x is the error in the measurement. If the measured value of x is used to compute another value, say f of x, we propagate the error. The difference between f of x plus delta x and f of x is the propagated error. We are carrying on an error. So, a formula here, f of x plus delta x minus f of x is delta y. So I'm going to clear the board here. We're going to go on to example 3. It says the measurement of the side of a square is found to be 12 inches with a possible error of 1/64 of an inch. Use differentials to approximate the possible propagated error in computing the area of the square. So we're saying x is 12. We're saying delta x is dx, which would be 1/64, plus or minus. So dA is going to be this derivative, which is 2x dx. So delta A would be approximated by dA, which is 2x dx. That's 2 times 12 times plus or minus 1 over 64. That's plus or minus 0.375 inches. Okay, differential formulas. Let u and v be differentiable functions of x. The constant multiple derivative of c times u is c du. Sum or difference d of u plus or minus v is du plus or minus dv. Product, the derivative of uv is u dv plus v du. We've seen that before. Quotient du over v is going to be v du minus u dv over v squared. So for number 4 it says, find the differential dy of the given function. So y equals x times the square root of 1 minus x squared. So dy would be x times ddx of 1 minus x squared to the 1/2 plus the square root of, well, I guess I can leave it as square root of 1 minus x squared ddx of x dx. So dy will become x times 1/2 times 1 minus x squared to the negative 1/2 times negative 2x plus the square root of 1 minus x squared times 1 dx. So dy equals, from here, negative x squared, because the negative and the 2 cancels with the 1/2, over the square root of 1 minus x squared plus the square root of 1 minus x squared dx. And that'll become negative x squared over the square root of 1 minus x squared plus the square root of 1 minus x squared times the square root of 1 minus x squared over the square root of 1 minus x squared dx. And that's if we want to combine them, common denominator. This could be a final answer if we wanted it to be. dy would end up being negative x squared over the square root of 1 minus x squared plus 1 minus x squared over the square root of 1 minus x squared. So we're looking at negative x squared plus 1 minus x squared over the square root of 1 minus x squared. So dy equals 1 minus 2x squared over the square root of 1 minus x squared dx. I'm going to go on to the next page, so feel free to pause if you need to. Volume and surface area. The radius of a sphere is measured to be 6 inches with a possible error of 0.02 inch. Use differentials to approximate the maximum possible error in calculating the volume of the sphere, the surface area of the sphere, and the relative errors in parts A and B. So r is 6 inches, and delta r is dr, which is plus or minus 0.02 inches. So first one, volume is 4/3 pi r cubed, so dv is going to be 4/3 pi times 3r squared. The derivative of r cubed is 3r squared dr, which is 4 pi r squared dr, which is 4 pi times r is 6, so 6 squared, times plus or minus 0.02, which is plus or minus 2.88 pi cubic inches. For this next one, for S, ds is going to be 4 pi times 2r dr, excuse me. That's going to be 8 pi r dr, which is 8 pi times 6 plus or minus 0.02, which is plus or minus 0.96 pi square inches. So we're talking volume versus surface area. Relative error would be dV over V. So that's going to be 4 pi r squared dr over pi 4/3 pi r cubed. Now in that, the pi's would divide out, r squared leaves an r down below, the 4's divide out, the 3 will come up. So we end up with 3 dr over r. That's going to be 3 times 0.02 over 6. It's 0.06 over 6. It's 0.01, which is a 1% error. And ds over s, that's going to be 4 pi, no, we said 8 pi r dr over 4 pi r squared. Well, 8 divided by 4 is 2. The pi's divide, r and r squared goes. Leaves us 2 dr over r. So that's going to be 2 times 0.02 over 6. It's 0.006666. That's going to be 0.67% or 2/3%. Either one of those. So we found our dV, we found our ds. Now it's dV over V, ds over s. And I put the dV formula over the volume formula, ds formula over the s formula. Okay, I'm going to go on to the next one. Feel free to pause that. Triangle measurements. The measurement of one side of a right triangle is found to be 9.5 inches, and the angle opposite that side is 26 degrees 45 minutes with a possible error of 15 degrees. Approximate the percent error in computing the length of the hypotenuse, and then estimate the maximum allowable percent error. Where's my B? Is it on the next page? Yes. In measuring the angle, if the error in computing the length of the hypotenuse cannot exceed 2%. So first of all, we have 26 degrees 45 minutes. That's 26 degrees plus 45 minutes times 1 degree over 60 minutes. That's 26 degrees plus 45 over 60. That's going to be 3/4, so plus 0.75 degrees, so it's 26.75 degrees. So our theta is 26.75 degrees, and then our d theta is 15 minutes times 1 degree over 60 minutes, which is going to be 15 over 60 degrees. That's going to be 0.25 degrees. So h equals 9.5 cosecant theta. So our dh is going to be take this derivative, 9.5 times this derivative is negative cosecant theta, cotangent theta, d theta. That's negative 9.5 cosecant of 26.75 degrees, cotangent of 26.75 degrees, and that negative just brought that out, times plus or minus 0.25 degrees. Okay, so our h, our dh comes out to be negative 10.4686. Now h is 9.5 cosecant of 26.75, which is 21.1065. Okay. Now our dh over h absolute value is going to be this negative 10.4686 over 21.1065. Take the absolute value. We end up with 0.495991. But this is in terms of degrees. If you want it in terms of radians, we would do 0.495911 times pi over 180 degrees, and we're going to be at 0.0087 or 0.87%. Because we really can't leave it in degrees with this in degrees here. Okay. I'm going to go on to part B on the next page, so pause if you need to pause. dH over h, that's going to be cotangent theta over d theta over cotangent theta. That needs to be less than or equal to 0.02 over cotangent theta. No, I'm sorry. No, got this wrong. First of all, what is our dH? dH, we're looking at the absolute value, dH is going to be negative 9.5 cosecant theta, cotangent theta, d theta, over 9 cosecant theta. And if we reduce out of this, the 9.5s and the cosecant thetas, because the absolute value of the negative goes away, we're left with cotangent theta d theta. And cotangent theta d theta needs to be less than or equal to 0.02. That's the error we want. So we want to know what our d theta can be that'll give us a 0.02 error or less. So d theta is less than or equal to 0.02 divided by cotangent theta. D theta over theta is less than or equal to 0.02 over theta cotangent theta. So the absolute value of d theta over theta is less than or equal to, or just less than, 0.02 over 0.02 times tangent theta over theta. So our absolute value of d theta over theta less than or equal to 0.02 tangent of 0.4669. And by the way, if we do 26.75 degrees times pi over 180 degrees, we get 0.4669 over 0.4669, and our d theta over theta, so this is the error with the d theta over theta, would need to be less than or equal to 0.021592, less than or equal to 0.02169, or 16, if you round it to that many places, so 2.16% in radians. Okay, so f of x plus delta x is going to be approximated by f of x plus f prime of x dx. We're going to finish this section off and then finish this chapter off by doing example 7. It says use differentials to approximate the value of the cube root of 26. So I'm going to scroll up, pause if you need to pause. So f of x equals the cube root of x. Now if we said x equals 27, we could say our delta x would be 1. or negative 1. 27 plus negative 1 is 26. So f of 27 plus negative 1 is the cube root of 27 plus negative 1, which is the cube root of 26. As we saw from just above, f of x plus delta x is f of x, is approximated by f of x plus f prime of x dx. So our f prime of x is going to be what? 1/3 x to the negative 2/3. It's going to be 1 over 3 times the cube root of x squared. So f of x plus delta x, now f of 26 is going to be approximated by f of 27 plus f prime of 27 times negative 1. So it's f of x plus f prime of x times dx. So we have the cube root of 27 plus 1 over 3 times the cube root of 27 squared times negative 1. Cube root of 27 is 3 plus 1 over 3 times what? The cube root of 27 is 3, 3 squared is 9, so times 9 times negative 1. So that's going to be 3 minus 1 over 27, and that's going to be 2 and 26/27. And that's approximately 2.962963. Okay, you can check it with the calculator. If you do the calculator, the cube root of 26 is approximately 2.962491. So we're close for 3 decimal places. And that'll do it for 3.9. That'll do it for Chapter 3. So we're going to get to Chapter 4 next, where we talk about areas and going the other direction. We've been taking derivatives, now we're going to learn some new tools. So I hope you enjoyed that. Thank you. Send me your questions.